Hello and welcome to the Daily Space for today, July 16th, 2018. I am Dr. Pamela Gay, and today I will be your host as we go on a fast-paced journey through some of what is new in space and astronomy. One of the things that we have discovered while doing this show is there's this fascinating difference in what news we get from what group, depending on what day of the week it is. On Wednesdays, Thursdays, and Fridays, quite often, our cup of press releases runneth over, and we're not sure how to get through all the news that's in front of us. Now, what we do in these circumstances is we turn to the archive, the log of all the new journal articles that have been posted for people to be able to read without having to have subscriptions to all of the different journals that are out there. Now, while the archive is something that's relatively straightforward to consume at the end of the week, it turns out on Mondays, on days like today, the archive is nothing but article after new article, and we drown in the journal articles. So it turns out Mondays, which are not the key day for getting press releases, are the day that all the new journal articles are out there. So if you're looking to keep up the same way I do, be aware, Mondays are your day to get all the latest journal articles. And pretty much the rest of the week, that's when you want to tune in to the press releases. Anyways, that was one of those interesting discoveries I made because it turns out you can do science anywhere, including in trying to figure out how to communicate science from your inbox. Anyways, on to my favorite story of today. This is a amazing image that was put together using, most of the big radio telescopes that are in nations that like each other around the world. This is a compilation of data that was taken using telescopes in the European Large Baseline Array Network, taken using the United States Very Long Baseline Array, using the Green Bank Telescope, pretty much all the big radio telescopes across Europe, across the United States, all of them work together to make this one single image. Now, looking at this, it's like, okay, it's a circle. Why are you excited? Well, the reason we're excited is this circle of radio data is all from one little radio loud galaxy whose information has gotten spread into a circle through a process called gravitational lensing. The way this works is if you have a foreground galaxy that we shall call the leveler, and you have a background galaxy, in this case the bottle cap. Right now, the bottle cap's light is fairly separate from the level's light. But as the bottle cap gets closer and closer, three-dimensional thinking is hard, gets closer and closer and closer to being directly behind the leveler, what ends up happening is the light from this bottle cap that is otherwise headed off in that direction is going to get gravitationally bent to come back towards Earth. In the case of a perfect alignment between these two things, in that unique situation of perfect alignment, you actually get a perfect ring of light being bent around by that foreground galaxy's gravity. Now, it turns out most alignments are just a hair off, and that just a hair off leads to arcs. Usually much smaller arcs, much patchier arcs than the one that we see here. This is one of the rare cases of having, more of the circle than you normally otherwise get to see. And because we can see more of the circle, we're able to measure the distribution of mass in our foreground object. It's possible with computers to say, if this foreground galaxy is shaped like a cigar, you expect the gravitational lens to look one way. If it is for some reason shaped like a smiley face, you expect the background galaxy to get warped another way. Well, in this case, we know that the galaxy doing the lensing is close to circular. And because of the precision of these images, we can measure exactly how close to circular it is. And this is extraordinarily important because it lets us actually measure how much dark matter there is that we can't see in luminous light images of this field. And this means we can map out that distribution of luminous mass with our normal light measuring telescopes, and we can measure the distribution of dark matter using the effects that the luminous plus the dark have on warping the background object. Using this, they have been able to figure out that the dark matter isn't a perfect sphere. It's actually patchy, it has clumps and lumps in it, and these lead to little tiny structures I know my eye can't totally pick out of this arc. So sometimes it takes using all the telescopes to measure all the stuff that we can't see with the telescopes, by looking for the effects that this unseen matter has on our luminous universe. So this is one of those kind of cool pieces of science where everyone was able to work together to help measure something that is a common question. It's is the dark matter clumping up into dark matter galaxies, small dwarf clusters of nothing luminous around our standard big galaxies like the Milky Way? The answer appears to be yes. Why, yes, it is. And that's kind of an awesome new thing for us to get to study. Now, moving a little bit closer to home, this is perhaps the ugliest picture you will ever see of the truly beautiful moon, Io, that is orbiting Jupiter. This little world was found 39 years ago to have still active and spewing out stuff and things volcanoes. And we've been following these moments of volcanism, these moments of eruption, ever since. And as we look to see how how Io is redecorated by all of these different volcanoes, we have, along the way, managed to discover that it's not just the known volcanoes that are periodically giving out new matter, it's also the unknown volcanoes. This particular image is one that is in the infrared. Infrared is a way that we can detect heat. In fact, if I point an infrared telescope at you, I am able to see the parts of your body that are warmest and coldest. Your nose hanging out on front of your face will appear to be a different temperature than your cheeks when you flush, than your chest, which is near your heart and your lungs and is always warm. All these things will show up in an infrared picture of you. Now, when we take infrared pictures of Io, we're not exactly measuring the blood flow, we're measuring the lava flow. And here, each of these hot spots, those indicate various volcanoes. The difference between the left and right side in this image is due to the left side being illuminated by the sun and thus having a warmer background temperature, and the right side being the dark side of Io in this particular picture, making it even easier to see the volcano stand out against its cold background surface. Now, there is a circle around this one faint little, blob of infrared light. And that faint little blob indicates the location that a new volcano appears to be coming into existence. So just like the Earth periodically springs forth new volcanoes, it looks like Io periodically springs forth new volcanoes. And next on our agenda is going to be figuring out how this happens on a world that we don't think, but we could be wrong, we don't think has plate tectonics like we have here on Earth. Now, I have one more story for today, and this for me is a sweetheart story. This is a mission that is finally given a launch date, and it is a mission not launched by a nation, not launched by a major multi-billion-dollar corporation. It is a mission being launched by a set of interested scientists and engineers working in Israel as what started out as just a team endeavor to try and win the Google Lunar X Prize. This little spacecraft is now set to launch in December on a Falcon 9 rocket. It is planning to touch down on our moon on February 13th, 2019. It will launch from Cape Canaveral, and I hope many of you have the chance to go see this. Now, Space.il isn't the only company that is going to be launching on this rocket. They are actually a secondary payload that just gets to tag along. This helps bring down their price because this particular mission, since it isn't government funded, since it isn't a major multi-billion-dollar company, this little mission, it has a budget of about $88 million that has gone into making it hopefully something that will land, send part of it to travel an additional 500 meters, and then send back high-definition video. Now, one of the things that's kind of frustrating about this sweetheart story of volunteers who formed a small company that built a small rover, or robot in this case, is this was built initially in hopes of winning the Google Lunar X Prize. But in March, Google ended this contest. It had been going for many years. It had many extensions. It turns out one of the big problems faced by many of the different companies trying to get to the moon was just not having launch vehicles they could launch on. Well, we've finally reached the point where Falcon 9s are launching frequently enough that getting a berth isn't all that difficult. But now that that problem has been solved, well, Google gave up on the project. So these guys are now launching for the joy of launching, for the science of the results they will get, and to be a new country exploring the moon. Space.il is a company of men and women, many of whom are young and enthusiastic, and some of whom are members of our community. And this wonderful group of people, their little spacecraft is going to be the first not built by one of the major world powers. In fact, Israel will become only the fourth nation to land on the moon. Of course, we have the United States and the Soviet Union / Russia, which have both been to the moon. China has joined us there as well. Japan has orbited the moon, but hasn't yet landed. So when it comes to landers, they're joining the world's superpowers in setting down on another world's surface. So I don't know about you, but I'm really looking forward to this mission, and we will try and bring it to you live from here at CosmoQuest, and I look forward to having members of the team come and join us on this show so that we can bring you some behind-the-scenes information. So those are today's stories. The Daily Space is brought to you by CosmoQuest. We are a project dedicated to getting everyone who, lets us get everyone involved in learning and doing science. We produce content like this show you've just seen, and over on our website, CosmoQuest.org, we have a variety of citizen science projects that you can get involved in. If you have a few spare moments, if you're going to be watching more shows here on Twitch, consider popping open another window and doing science while you watch, while you're bored, in all those stolen moments that might otherwise go to a game of solitaire. Instead of doing solitaire, do science. Now, our show is sustained by you. Please consider giving us a follow. They're free. Your subscriptions really keep us going, and every bit really matters. So if you have any questions, go ahead and at me, and I am going to go ahead and work on answering them. So I see from Hanny, are they going to do any science or just prove that they can get to the moon without governmental funding? I knew this answer once upon a time. They're not just landing for the sake of landing, although that is entirely cool. They do have specific mission outcomes. I don't remember if their mission outcomes are strictly technological tests and tests of our ability to do specific things that will be necessary to do science with bigger vehicles, or if they have historic goals. There are a variety of different Google Lunar X Prize teams that have continued their work. We have both Moon Express and Astrobotic as two of the other large teams. And across the teams, we see technology goals, we see commercial goals, and we even see history goals with the idea of imaging Apollo landing sites. Not out of the question. So it's not a do it for the sake of doing it. It's a doing it for the sake of learning about what's possible. I wish I could give you greater details. As I said, I need to have some of the team members join us here on this show to answer some of these questions for you. Okay, looking to see what other questions there are. So Kaymore asks, are the volcanoes on Io similar to the ones on Earth, or are they different from the tidal forces on Jupiter? Sorry. Well, volcanoes come in many forms. There are those that eject lava, which is molten melted rock, and there are those that eject ice. So we have cryovolcanoes and we have classic volcanoes. The volcanoes that are classic volcanoes, like we have here on Earth, also can be broken down into other kinds of volcanoes. We have hotspot volcanoes, such as those in Hawaii, that as the crust of the Earth moves across the hotspot, new volcanoes pierce through that crust, creating new islands. We also have volcanoes that are part of the crust and exist at those points where two different plates are diverging or converging. This is such as the volcanoes that we see along the Ring of Fire in Indonesia, Japan, Alaska, the west coast of the United States and Central America, and of course all the way down the coast of Chile. All these different kinds of volcanoes have one thing in common. Molten stuff from the core of the Earth is escaping through the surface. The molten stuff in the Earth is liquid due to, well, heat that's still trapped in the planet from when it formed, and also from the heat of nuclear decay that is going on within the mantle and crust as things like uranium decays over time. All these different things create a warm planet on our planet. Now, with Io, I don't think, but I could be wrong on this, that we can distinctly say this is a shield volcano, this is a cone volcano, and I think most of them we've determined are hotspot volcanoes, but the way that Io is made to have molten stuff on the inside is where the radical difference occurs. Io's tiny. Io should totally be solid all the way through, but it's not. And the reason that it's not is due to constant gravitational squishing and pulling apart that occurs as it gravitationally interacts with Jupiter and the other Galilean moons, Callisto, Europa, Ganymede. It's orbital resonance in combination with Jupiter being large. Squish it like a squishy ball. And here's an experiment you can all do at home. Find yourself a racquetball, a super ball, any kind of a rubber ball that will deform on impact and doesn't have an insulating coating on the outside like a tennis ball does. Bounce that ball madly. I encourage you to find a small child to do this for you, or to have one of the balls that's attached to a string and you just bounce it on a small board. If you bounce the ball fast enough and long enough, you can tangibly feel it getting warmer due to the constant deformation and stretching that the ball undergoes. It's that same compress, stretch on Io that is generating the internal heating that is generating these volcanoes. I hope that kind of sort of mostly answered your question. Clearly, we need more high-resolution detail to do better comparative volcanology between our world and Io and all the other worlds out there that have volcanoes. We don't know if there's active volcanism on Mars. We know Mars had a very active past, and even our own moon at one point in its past had volcanoes on its surface. So looking to see what other questions there are. So Keeper of Maps is asking, what is the temperature of the hot spots on Io? So let me switch over to bringing that image back up. One moment while I reconfigure my screens. So this particular image is in really weird units of megawatts per, it looks like steradian per meter squared, which is not a unit that any of us are capable of thinking in. Let me pull up the press release and see if the press release goes into, well, better units. So the hotspot is about 200 miles or 3 kilometers across. Io has 150 active volcanoes that we know so far, and it's an estimate of 250. And no, they did not translate these temperatures into anything useful. So I'm going to attempt to Google it. Let me see what I can get. So we have milliwatts per mysterious unit of SR per meter squared. Let's see what we can get out of Google on that. I found a site in French. Okay, so it is milliwatts per steradian per square meter. I don't think it's going to let me get there from here. I believe from what I'm looking at that this particular image is one that is strictly measuring the amount of light energy coming off the surface. But let me see if I can at least get you information from another source. So according to an article on space.com, Io's surface temperature averages about 202 degrees Fahrenheit or 130 degrees Celsius. This leads to sulfur dioxide snowfields, actually. So this lava does have a different composition than the lava here on Earth. It's the molten version of the rocky stuff Io is made of, which is different from the rocky stuff Earth is made of. Let me see what other questions you have. Oh, I see the question of what's a sterradian. Okay, so you remember how in geometry class in high school, your teacher tried to convince you that there was these more useful things called radians that you should be using instead of degrees, and that there were 2 pi radians in a circle, even though a circle is 360 degrees, and that is a perfectly understandable unit of measure. Well, sterradians are the surface area version of radians. So, for instance, there is a theater at MIT that has a roof that is a certain number of sterradians in size. It's a domed roof. I believe that there are 4 pi sterradians in a sphere, but let me look that up. Sterradians in a sphere. I think in degrees. It's discussed as a solid angle is how they look at it. I remember it as the horrifying thing I had to learn how to use. I did not like and continue to not like. And there's even a really bad Wikipedia page on it. So sterradians are apparently so disliked that no one did a good Wikipedia page on them. Anyways, it's just the measuring surface area in radians kind of thing. Yes, it's basically 3D radians. So looking to see. So CosmoQuest, if you go up along the Terminator, looks like more hotspots about the central one. So the question becomes one of how many of these did we know about versus how many of these were unknown. In this particular image that's littered with hotspots, only one of them wasn't known, and that's what's exciting, is finding new things we don't know about. Yeah. 202 Fahrenheit. Okay, so this could be a case, keeper of maps, of once again, a press release did really bad unit conversions. Okay. Yes, Hanny, I'm totally going to be the change I wish to see in the world when it comes to using things other than sterradians. So it depends, Larry, on if you're trying to measure volume, which would be 3D, or surface area on a 3-dimensional surface. So sterradians is a unit of area on a spherical surface, just to be as confusing as possible. And yes, a sphere subtends 4 pi sterradians. I finally found it. Yeah, it's another SI measurement. I generally love scientific notation, but anything where all of your numbers involve a pi, I like my numbers more rational most of the time, thank you and please. Yes. Yes, the size of a constellation can be measured in sterradians, that is true. And all the constellations should add up to 4 pi sterradians in area. And sterradians is radius independent. So a sphere I can hold in my hand versus the sphere of the Earth, both of them have an area of 4 pi sterradians. Okay. Yeah, translating, Dave, is definitely a challenge when it comes to units. My brain has gotten very good at having a generic understanding of both Celsius and Fahrenheit, so I don't have to do unit conversions. I know low 20s is probably going to be upper 60s, low 70s in Fahrenheit. I know that over 30 is going to be 90s and hundreds, and 40 is all of us should die now, 110-ish. But there's that ish, because it's my body knowing where it's comfortable instead of knowing precisely what the two different temperatures are. The key is to develop that ability to hold something up and go, this looks kind of like 10 centimeters in length, or 7 or 8 inches in length, and then finding the ruler and seeing, are you right? So for instance, I'm now going to pull out a ruler and go, wow, I was totally wrong on number of centimeters. This is about 18 centimeters, but I was equally wrong on number of inches. So I can't judge the length of things. But for temperature, I have that intrinsic ability to know how miserable I am at any given moment. Yeah. So K Moore, I don't think I've seen your name before. Welcome. K Moore says, so we have pics of Io from several probes, but the surface is constantly changing. How long till the first pic we took years ago will be unrecognizable to what is actually there? So yes, we have myriad of photos taken over many years. I'm going to try and find a particular volcano that we've been trying to chase the rate at which it's resurfacing the surface of Io. This is, and I'm trying to find pictures from different years. So Patera, Loki Patera is the name of the volcano, and it was first imaged by Voyager 1. And we've been following it ever since. And I've seen lots of estimates on how fast it's eating its part of Io. But I don't remember the how fast. So let me see what I can find. The amazing thing about when we live is our understanding of all of this science is changing faster than many of us are capable of sticking the new data in our head. So I'm capable of remembering that it's Loki Patera that is so darn cool, but other things are a bit more challenging for me, such as remembering just how much lava comes out of it year after year after year. I'm not finding anything quickly. I will try and come back with that information for you on another day. Yeah, things named Loki are particularly interesting, it seems. Okay, what other questions do we have? So Henny's Vorverp is asking, can Juno take pictures of Io? Well, yes, in the infrared, it already has. That's what we just looked at. I think you mean, can JunoCam take pictures of Io? JunoCam is an afterthought instrument that was added to the Juno mission to allow everyday people like any of you to suggest particular targets they wanted to see, well, imaged on the surface of Jupiter. Now, I don't see why it couldn't be used to observe Io, although I can see why you might not want to use it to observe the surface of Io. The way the spacecraft is configured, you have to rotate the spacecraft to get particular instruments pointed at that thing you most want to look at. So if you can imagine that you have an infrared camera in your right hand, a regular camera in your left hand, you have to rotate to get things in field. With an infrared cam, when we look at Io, we can see all these details of where the volcanoes that otherwise would be lost in the brightly colored surface are located. With a visual camera, we get very different information that isn't quite as useful scientifically. So the question is, can a bunch of people make a wish on what Juno cam should be pointed at and convince the team to point it at Io? So looking to see if there's anything else. So Graham HW, another new name, I think, is saying when they next send a probe to Saturn, they should send CubeSats with it to explore some moons closely. And this is the kind of justification for the fact that the InSight mission, currently on its way to Mars, arriving in November, has with it 2 CubeSats, A and B. And these 2 entirely boringly named CubeSats are testing the technology, testing the limits of what we're able to do on interplanetary missions with this little tiny technology. We're going to test out what's possible going to Mars, which is fairly nearby on the planetary system size of things. And once we've mastered it with Mars, once we've tested the technology with Mars, it starts to become possible to imagine going to other worlds. Now, with the moons of worlds like Saturn and Jupiter, we have some added concerns, and Dave Killens just completely brought it up, and this is the risk of contamination. Some of you may remember back in, I believe it was either late 2002 or early 2003, the Galileo mission came to an end as they purposefully plunged the mission through the atmosphere of Jupiter. Last year, we had Cassini do the exact same thing. We brought the mission to an end by purposefully plunging it into the surface of, in that case, Saturn. The reason that we're doing this to our spacecraft is, one, to get data on the science of just how low to the surface can you get and still send data back. It's allowing us to measure the pressure density changes over depth with these worlds. It lets us get shockingly close in photos of these worlds. Well, that's the scientific reason we do it. The moral reason, the also biologically scientific reason that we do this is we don't want to kill things that we don't know about yet. We learned in our own human history that as people from different parts of the world first come in contact, we bring germs to one another. And our different environments, well, they may be completely friendly to the natives and completely deadly to the visitors. In Papua New Guinea, there are areas where the locals don't get sick from the water, but the flora and fauna occupying that water will very quickly either kill a European or make them wish they were dead. This is due to differences in immunity, differences in what we're capable of dealing with. Now, if we have problems just between going from one place on Earth to another with differences in immune system, the differences in immune system between critters that evolved on Earth and critters that evolved under the ices of Europa and Enceladus, any of these other worlds that are thought to potentially be home to life, Titan, well, an unsanitary probe could kill all that life before we study it. That would be bad, sad, many other things. So we try and figure out how to sterilize spacecraft, but there's limits on what we can do while also creating a spacecraft capable of making the journey. There's some life forms that don't die if you radiate them, and there are some circuits that do die when you radiate them. There are some life forms that are totally cool with extraordinarily high heat, which the plastics in a spacecraft may not survive. There are some life forms that are totally good with being frozen. And while spacecraft are generally totally good with frozen, it is really bad for their batteries. So there's all these different ways that we can kill life and also kill our spacecraft. So trying to create things that are completely clean, we're not there yet. We haven't figured that out yet. And for now, we are extraordinarily cautious in how it is we send spacecrafts out to explore other worlds with cameras. Bring back photos, not critters. And so in this particular case, something like Cassini, Europa Clipper, Galileo, these are very well-tested technologies. Cassini was built on the same technologies that originally were used for the Mariner probes, the Voyager missions. We keep evolving each new generation, but it's kind of like the difference between a 1988 Honda Civic and a 2018 Honda Civic. They're still built on the same bones. This is solid technology we trust. CubeSats, totally new technology. And we don't yet trust ourselves not to crash a CubeSat, which by definition will not be completely sterile, onto one of these potential life-having moons. So until we thoroughly test and we have complete trust in our CubeSats, it would actually be very irresponsible of us to send CubeSats to these worlds. Now, hopefully, just as this transition from Mariner to Voyager to Cassini has happened during some of the lifespans of you out there watching, hopefully within my lifetime, we'll see CubeSats go from kind of sort of trustworthy to rock solid technology that we're using to explore our solar system at new and lower costs. So looking to see what other technologies we have. Hello, the sub and for the sub and follow. Welcome. Glad to see you here. So looking to see if we have any more questions. Larry is asking if we have any news on the bacteria that's growing on the outside of the ISS. I'm sure some folks have news. I haven't seen a recent journal article in any of the journals I typically read, which admittedly don't often have astrobiology articles, and I haven't seen a press release. So feel encouraged to go Google and bring us back the information on what you find. There's so much science going on every day that I don't think any one person can keep up with all that is new in how we understand our universe. Scientists don't know everything. We just try to know everything and fail miserably and keep trying every day that we're alive. Yes, drone and smart swarm. I'm not sure if technology is the right word or software is the right word. They will definitely increase what we can do with CubeSats. Swarm algorithms are kind of amazing. For those of you who don't know about them, it is the ability of independent drones, whether they be soccer-playing robots or flying drones, to monitor the activities of all of their kinscraft and act like a swarm of birds, a team of soccer players, and figure out how to self-assemble and self-assign individual tasks to accomplish a job. It's really cool work that's being done. Yes, Guido, CubeSats are the future. It just is going to take time to really master what's possible. And yes, Angry Chef, the idea of self-organizing robots is somewhat terrifying. There are times when I, for one, welcome our robot overlords of the future, but also don't want to become a power source living in the Matrix. Yes, there are some Lego light sets now for animating butterflies, and there's actually folks working on how to build very simplistic sports teams using Lego robotics. Yes, they do have these self-organizing network protocols. We are there. It's not solid, it's not amazing, but we are there. These are the kinds of things that students studying robotics in universities today are doing as part of their in-class programming assignments. So yeah, it's a crazy and awesome world. So if there's no more new questions, I am going to remind you that we bring you the Daily Space every Monday through Friday that isn't a major holiday. And we're here as your go-to place every day at 1 p.m. Eastern, 6 p.m. London, that's 10 a.m. Pacific. And I hope that you will give us a follow, that you will find out exactly when it is you can tune in. And with that follow, you'll get notifications of all the other programs we do. We hold office hours, we teach basic astronomy courses, all sorts of different things are going on here on CosmoQuest X. And I invite all of you to come here and learn and go to cosmoquest.org and do. So I'm Dr. Pamela Gay. I'm glad I got to spend this time with you, and I hope you will be back tomorrow when I'll be back. Give us a follow. Use a subscription to sustain our efforts. And remember, every bit counts. We're part of the nonprofit, the Astronomical Society of the Pacific, and we're working in collaboration with the Planetary Science Institute and Youngstown State University. Thank you, and wherever you are in the world, have a fabulous morning, evening, or afternoon, and remember to sometimes look up. Bye-bye, everyone.